Recording. Okay, so welcome everyone to another session of NL seminar. Today, our guest is Dr. Svitlana Volkova. So we have a few guests coming. Okay, so let me read the speaker bio. Dr. Svitlana Volkova is a chief scientist in decision intelligence and analytics in the National Security Directorate of PNNL, where she is leading the lab's internal mega AI investment focusing on developing and deploying massive scale foundation AI models for science and security mission areas. Since joining PNNL in October 2015, Dr. Volkova was responsible for over 10 million in direct sales and has served as principal investigator or project manager on more than 10 internally and externally funded projects, including 2 DARPA and 2 NNSA projects focusing on advancing various aspects of AI, such as natural language processing, machine learning, deep learning, AI test and evaluation, and causal discovery and inference. Svitlana has authored more than 70 peer-reviewed conference and journal publications. She serves as senior PC member and area chair of top-tier AI conferences and journals, including AAAI, WWW, NeurIPS, ACL, EMNLP, NACO, ICWSM, Nature Scientific Reports, PNAS, and Science Advances. In 2016, she received the prestigious National Security Directorate Author of the Year Award for her outstanding number of top-tier publications in AI. In 2019, Dr. Volkova received the Ronald All Brodzinski Early Career Exceptional Achievement Award for her leadership and scientific contribution to the fields of computational linguistics and computational social science. She received her PhD in computer science from JHU, where she was affiliated with the Center for Language and Speech Processing and Human Language Technology Center of Excellence. So please welcome Dr. Volkova for this seminar talk.
Thank you so much for the invitation. It's my pleasure to be here. I haven't seen many of you for ages, and it's truly my pleasure to be here. And I hope this will be an engaging talk. Feel free to interrupt me anytime to ask questions. And today I'm going to talk about augmented intelligence for national security, focusing on two projects and 2 application or mission areas, cognitive security and resilience and nuclear non-proliferation. My team is responsible for human-centric AI for national security in the lab. And what we do, we develop decision intelligence capabilities to explain, predict, and prescribe complex systems and behaviors related to national security challenges in the human domain and beyond, with a focus on cognitive security, non-proliferation, biosecurity, and climate security. These days was the new investment that I haven't planned to cover in this talk, but I'm happy to talk about it later. So what we have developed in the last 6 years includes capabilities for cognitive security and resilience, a variety of predictive analytics where we anticipate the future, content intelligence capabilities like natural language processing or image processing, prescriptive analytics, which is our causal work that I will talk about today. A lot of trusted and responsible AI capabilities where we really evaluate model performance and model behavior. We have a variety of tools for that. We need to make sure that the technology that we develop, people can trust and the end users can trust, and we develop them in a responsible way. And finally, a new area is augmented intelligence, which is human-centered partnership model where the machine is augmenting the human with the ability to make decisions faster and make more optimal decisions. So it's not only decision-making, but it's also reasoning at scale. There is one thing that if you develop a deep learning or natural language processing, a machine learning model, and you put it on the shelf and it's not usable, there is another thing is how are you going to wrap it and make sure that you're developing this augmented intelligence to help the end user to achieve the goal, right? So, and that's what I'm going to demonstrate a few things. So in this talk, I primarily wanted to focus on on two areas, cognitive security and resilience, and outline our approaches to detect, characterize, and defend against influence operations and disinformation campaigns. And I will show you what techniques we're using to understand audiences, characterize the information environment, and discover causes and effects in information operations data or human behavioral data. And another project is related to nuclear non-proliferation. So on that project, we are developing AI-powered augmented intelligence capabilities to detect, anticipate, and reason about proliferation expertise and capability development globally by learning from massive scale, unstructured, dynamic real-world data, and specifically in this case, it's scientific literature. So these are the two parts of the talk. So, I mean, I don't think for this audience, I really need to give you like a one-on-one about information campaigns. You know all about it. And there are many types of information or influence campaigns, whether that's domestic or foreign influence operations, but they range from less deceptive to more deceptive, and the intent behind each campaign is different. So, for example, during intimidation campaigns, there are a series of actions which are intended to harm or upset someone or to make other people to have a low opinion about them. These campaigns are known as hate speech campaigns. There are persuasion campaigns and polarization campaigns that are usually happening during the elections. And there have been many evidence of these campaigns outside the US. For example, persuasion campaigns include actions of a person or a group of people attempting to get others to adopt a position and propagate it. And like vaccination campaigns, for example, are these types of campaigns. And then if you kind of move from these campaigns, intimidation, persuasion, and polarization into well-known misinformation and disinformation campaigns where the content is spread is not true, but in the case of misinformation, it's like there is no clear intent to deceive and it can be spread unintentionally. But with disinformation campaigns, like we know that there is an adversary who is sharing this content and there is a purpose behind the sharing and there is an intent to deliberately share this information. So our team did a lot in this space. We published more than 30 papers, peer-reviewed in different venues. And we kind of touched a lot of these campaigns. And many of this work is coming from a DARPA Social SIM program that many of you are familiar with. So in terms of intimidation campaigns, we analyzed the diffusion of software vulnerabilities across 3 social platforms, Twitter, Reddit, and GitHub. For the persuasion campaign, we looked into cryptocurrency pump and dump schemas, and we analyzed data on Telegram and Twitter. For disinformation campaigns, it's a recent work published by Nature Scientific Reports. We analyzed information diffusion during protests in Venezuela on both Twitter and YouTube in 2 languages, English and Spanish. And we looked into the different communities, English-speaking versus Spanish-speaking communities, and their contribution towards the information diffusion. We looked into gatekeeping and information dynamics and recurrence across these different communities that are speaking different languages. Another disinformation campaign is about white helmets in Syria, where we have a few data sets, Twitter and YouTube, and we analyze information spread in English and Arabic. And finally, the work that I'm going to cover in this talk is our most recent work on misinformation campaigns about COVID-19 narratives. And we looked into Twitter and Reddit, and I'm going to cover Twitter here in this talk just to demonstrate you the capabilities with a few examples. So what our techniques can do. So we really can assess information spread and engagement at scale in real time. And there are different types of assessment we can do. The first one is general engagement, right? How does the content spread? How far, how fast, how equally, and for how long? Another one is recurrence. So this is information dynamics. Can we measure explicitly recurrent patterns of engagement? The next one is network, very, very well known and very simple, right? So what are the social network characteristics and the community properties during these information campaigns? In addition to this information environment, right, information diffusion, we also can characterize the cognitive domain, the cognitive environment. We can analyze audiences' characteristics and their group properties, like reactions and demographics and perspectives, you name it. So, and finally, on top of all of that, we're able to generate causal explanations and actually demonstrate why some content spreads and some doesn't spread. And I'm going to cover all of it using the misinformation, COVID-19 misinformation campaign example. But let me maybe walk you through this tool. Let me know when if you still see my screen. Do you see my screen? Okay, good. So this is public. Actually, you can go and check this link. We developed it when the pandemic started. So I remember we went home in March, and then in the end of May or something, we already had that tool. And that tool was developed under another DARPA program, IPI, DARPA Ground Truth. We had the brain behind the technology. So we did have the NLP and the deep learning models behind each of these analytics here. And then what we did together, we just put that interactive visualization together to show the purpose of the tool. And this is an example of augmented intelligence where AI is augmenting the end user and augmenting the human and helping the human to make decisions. So this tool was done for COVID-19. We took Twitter data, 5.5 million tweets in the first couple of months during the pandemic. And then we predicted geolocation, we predicted user reactions and user perspectives and psychodemographics towards different non-pharmaceutical interventions, like social distancing or containment measures. So imagine you're the governor of California, right? And you want to know what kind of interventions are happening during the pandemic, and you want to see how many deaths and confirmed cases in your state. So all of these lollipops demonstrate different interventions for your specific state. And then if you are, as a governor, if you're interested how my people are reacting or what are their perspectives towards different interventions like social distancing, you can click here, and this is the taxonomy we developed. And then this is there behind it is the NLP model that is basically classifying different tweets into different categories here. So let's say you're interested in social distancing. And then when you click, you see that your user reactions are changing. So you kind of see the temporal evolution here. And as expected, primarily people are neutral rather than against or in favor. But as a governor, if you really want to see the dynamics of your like against reactions versus in favor, you can select charged reactions. What you can also do, you can get a summary. So for California, you see people are primarily in favor of social distancing, similarly to Ohio, but Ohio has more appreciation than California. Florida is half and half. And then in addition to that, you can also look into what are the perspectives that people are expressing towards the agents of the tweets versus the topics of the tweets. And you can imagine agents are primarily governors and the president, the actors, and the content, the theme is masks and not, back then not vaccines, but different types of topics that people are discussing. And you see that in California, people are primarily positive towards the agents and neutral with a little bit of negativity, and there is more negativity towards the theme, right? And in addition to that, you can also analyze psychodemographic traits. So we using deep learning models to automatically infer user gender, income, age, and education. We binarize it and we report our findings on the aggregate. So we don't predict we don't report gender for Jane Smith. And all of this data that goes here is anonymized, right? So we don't know who the user is. And then you see the outer circle is the predicted gender or predicted income distribution. The inner circle is the census data. But what's interesting here is that you can contrast and compare user perspectives and reactions across your populations, right? So you can say in California, male population that is represented here on Twitter expresses more elaboration than female population. And then let's say people who are I don't know, people who earn more money, they express more disagreement with social distancing than people who earn who with lower income, right? And then you can just basically explore more. You can look into movement restriction. You see how things are changing, and there are more charged reactions. You can go to a different state, like to Washington, and you can see how the people are reacting in real time. So again, this demo is available, and this is the reason I wanted to show you this, is because it's an example of an augmented intelligence that helps the decision makers in real time, right? This can also be used effectively, if we go back to the slides, to assess influence campaigns, right? To assess the cognitive domain during influence operations and information campaigns. And then behind each of this analytic, there is an AI model, right? So for psychodemographics, and I'm listing links here, but for psychodemographics, I believe it's a CNN-based model. In this case, binary grouping of your subpopulation. In addition to that, I haven't showed you, but we do have ability to predict the first language of the user, right? So I'm a native Ukrainian and Russian speaker, and the way that I use my English is very revealing of my first language, of my native language. And then for perspectives, we're using connotations. It's a rule-based model, but we have this model developed for more than 10 languages, so it's multilingual. And for the reactions model, I believe it's an LSTM that was developed during the pre-transformer age. So different reactions, we basically classify in tweets into 3 broad categories: in favor, against, and neutral. And you can also look into more detailed fine-grained acts like disagreement, agreement, elaboration, question, answer, and so on and so forth. So for the assessment of the cognitive domain, we have this AI-based technologies, and then we have the information domain, right? So information diffusion, which is primarily coming from DARPA Social Sim, where we measure the speed and the scale and the audience size and different network properties, connectivity and polarization during the information campaign. So let me give you an example of how this technology can be used. Again, during the beginning of the pandemic, there was, and even right now, there is a lot of misinformation that is spreading. But then we did this analysis a year ago when we looked into Twitter for over a month, between March and the mid-April, and we looked into several specific narratives or topics, if you wish, with different intent. So some topics had an intent to spread fear or to make profit or to influence politics, right? So we have 7 misleading narratives that are coming from the Princeton narrative annotation shared source. And then, so basically these are journalists and scientists who are annotating different tweets and different content with not only the intent, but also like whether it's misleading or false. So we took a few example narratives and we went in this with sample Twitter data, and we measured the core properties of this information spread. We measured how we measured the recurrence, and we did the assessment of the information environment through the network analysis. And this is these are the key findings. What we found is that the highest number of shares and audience size and speed and disparity, so basically the most viral narratives are those with the intent to spread fear, which makes sense, and those with the intent to influence politics. And then we also found that the networks with the largest diameter and connectivity are those that are targeting full national lockdown. Everyone was concerned about it during the beginning of the pandemic, and politically related, virus created to weaken Trump. And finally, we found that if you look into the cognitive domain, and if you look into audience reactions and the sentiments, primarily they are neutral towards the themes like vaccines and masks, but they're more positive towards the agents like people and organizations and locations, different named entities. Let me go a little bit deeper. This is the high level. So when we did the analysis, we generated this really cool visualizations where we group narratives by the intent, right? And then you see these are radar plots, and then on each axis you see different information diffusion measurements So two of them are measuring the disparity of the spread, Palma and Gini coefficient. The easy measurements include the number of total shares, the speed, and the number of users, the audience engagement. And then you can see really clearly here that some narratives like COVID was caused by 5G, which is blue on the left-hand side, has the highest disparity and the highest number of shares and speed. Narrative that is talking about full national knockdown, people are the most engaged with it, right? And then in terms of the narratives, the two narratives that are intended to make profit, they are the smallest. They don't spread far, they're really tiny compared to narratives that target to spread fear and influence politics. And then we also made this network visualization of the co-occurrence of these discussions, right? So again, it's colored by the topic or the narrative, and you see that there is this big blue blurb, a highly connected component, and this corresponds to virus created to weaken Trump content. And it has like thousands of nodes. It's very tightly connected, and it has a large diameter, and the average distance to travel in this case was 5 nodes for the information. And then another example I want to show you is the perspective dynamics towards the agents and towards the themes, and they are very, very different. So if you see, depending on the intent, right? So you see, for example, narratives with the intent to spread fear, they're primarily positive, then neutral, and then negative. But then if you go to the theme, from the agent to the theme, you see that it's very neutral, right? So across all of the narratives and intents. And all of this.
Sorry, on that previous slide, what is the x-axis?
So this is the number of tweets.
So wait, 9, 16, 23, 30, that's 10,000 or times what?
Hold on, I see 1,000, 500, 1,000, 1,500.
No, the x-axis.
Sorry. Yeah, x-axis is time. My apologies. Yeah, so this is
like
April.
Day of the month.
Yes, this is April 2020. Yes, in the end. Sorry, tiny. Yeah, over time. And then all of these people are behind this great work, the social sim performers and our collaborators for the developments of the cognitive domain. And then the next part of my talk, I want to focus on the causal work. So there is one thing if you're able to answer the what questions, and AI can help you to answer the what questions, how information is spreading, who is sharing this information, and so on. But what we actually want to answer is the why questions. Why is it spreading? What makes it to spread? What makes people to be more susceptible or less susceptible and share this information? So these are the, again, bluff up front. So these are the key findings. What we found is that being a verified user affects the engaged audience size, and content type, like the narrative, affects polarization and diffusion lifetime and disparity. And the presence of named entities in the tweet affects the diffusion lifetime, for how long it lives. And finally, the tweet is mentioning clear moral foundations. It affects the scale of engagement. So basically how much it's reshared. And let me tell you how we did it. So this capability is coming from DARPA Ground Truth program, where we developed technologies to perform causal structure learning or causal discovery and causal inference using treatment effect estimation. And usually the way that people try to get closer to causality is through randomized controlled trials, where you have the control and the treatment, and then you have mean outcomes and you get the average treatment effect. But in many cases, this is not possible or not ethical or unachievable, right? That's why there are these techniques that exist that can allow you to learn this cause and effects from observational data. We developed and published at NERPS, I believe 2020, a paper on a causal ensemble where we take primarily Perl stuff from that school, and we created an ensemble model that relies on more than 10 different causal discovery algorithms, and we rigorously evaluated it on simulated data. And that's described in this paper, Evaluation Algorithm Selection and Ensemble Methods for Causal Discovery. And we applied these techniques here. But in addition to causal structure learning, we also did treatment effect estimation using the tool that, again, we developed under the DARPA Ground Truth. The tool is called WAIN, Visualization and AI for Natural Experiments. It was recently published at a top-tier VIS conference, and we also have published a lot of really cool graph comparison tools where you have multiple graphs that are coming from like different algorithms. Let's say for treatment effect, we have propensity score matching, causal forest, and vein. And then we can easily compare the agreement of these algorithms on the data. So these are the techniques that is behind the findings. And again, as I said, our intent is to answer why questions and how questions. What we did to prepare the data, we annotated and extracted message properties like moral foundations and perspectives or sentiments. We extracted different biased language, named entities, and temporal patterns of the messages, the narrative type, the intent, and so on, right? Everything that you can extract from the language from the message. Then we also extracted author properties or source properties, different things from the metadata. You can think about followers, friends, the ratio, the bot score, whether they're kind of verified, when was it created, a variety of characteristics of the source. And then we also use the measurements, right? The diffusion speed, lifetime and scale, network polarization, as the outcomes, right? So in this case, think that you can, for example, use one treatment in context of the covariates, right? All of the message properties and user properties, and you can measure the effect of this treatment on the outcome, right? And the outcome, for example, is the speed of spread, right? And these are the main findings here. I'm showing you this for the COVID misinformation campaign. So different nodes. This is coming from the causal ensemble model, where we color the node, whether it's an author or the message or content or the outcome, right? So if you look onto the right-hand side, you see that message characteristics affect causally the volume of spread, lifetime, and the quality of engagement, right? So you kind of see that narrative affects the post-lifetime or post-outcome Gini and Palma, which is the disparity of spread, and the message care, right? So care, moral foundations, they affect how many reshares will happen of this tweet. And then if you look into the audience properties, you see that audience properties primarily affect network characteristics and audience size and the speed of the diffusion, right? So if the user is verified, the message, it affects the audience of this message, right? The perception. And then there are a lot of message properties like the length and the posting lifetime and different attributes of the user that affect the node degree. And then we also see that when in the day the message was posted, it affects how fast it spreads, the speed of spread. So I think this is the last one here. And again, the Ground Truth team is responsible for all of this great science. And I should probably stop here before I move to the next part of my talk. And are there any questions?
Yes, a lot. So you were saying that you see these things affect this other thing, right? So presumably sometimes you find that a property does not affect an outcome. So when you say affect, what do you mean? Like how do you determine that something affects?
So we run an ensemble, a causal ensemble model that finds the cause and effect between different like variables, right? And that's, I mean, as I said, it's not like we run one algorithm. I think like these algorithms are very brittle and they have high disagreement. That's why we run an ensemble. And then when multiple algorithms, so basically we have a weight on the edge, if you wish. And this is just one way to show, I should have shown more here. I should have thought that, I mean, your audience is very interested in causal discovery and inference. So when you do causal structure learning, you kind of take your observational data, a bunch of variables, right? And in our case, we basically had more than 100 covariates. It's a high dimensional space for the causal work, for the causal discovery. So when you take this observational data, you're trying to learn the whole cause and effect within the system, right? So all of the relationships between all of the nodes in the system. And this is one way. But another way is just basically do treatment effect estimation. Just take one variable, take another outcome, right? In context of all of the covariates, you can measure treatment effect, and it will give you a value, right, of the effect of the treatment on the outcome, right? And I haven't shown this result, but I would be happy to share if you're interested. And for that, I'm going to show it actually next in the in this exploration with this work. But did it answer your question, John?
No, so I mean, like, do you have training data of what the effect should be, like, in order to build this? I just don't understand. Like, you're saying, like, you predict, okay, if you have this, this will happen, but like.
No. I mean, this is observational data, right? So we don't have the ground truths, but when we, the reason I mentioned that NERP's paper is that we validated that technology, right? The ensemble model on simulated data when we knew the ground truths, right?
Right.
And then, right, so there are like F scores and all of that beautiness for, yeah.
Okay, I see. Great.
Yeah,
and then, and the inputs to these are themselves the outputs of models like the moral foundations or the gender or income estimates, right?
Yes.
And those are pipeline. It's not one continuous model that you're optimizing, right? You've separately learned an income model or something like that, and you just use that statically.
Absolutely.
Okay. And those are all coming from your team, or are those like pulled from other areas too?
No, both score is coming from Bottometer, but that's it. I think in this case, the rest is coming. I mean, moral foundations is a public resource, right? So the sociologist came up with it. Biased language lexicons are coming from Stanford, and we extended it. There was a work with Yejin and her former PhD student, Hannah, who's at Google right now. We took like basically public resources of like different verbs and adjectives that are that reflect subjective language and subjectivity for deception, right? And we extended it, and we publicly released. Yeah.
Got it. Okay. Cool. Thanks.
I wanted to follow up on that question.
Yes.
Alex, you go first.
Oh, okay. I'll be quick, just because it ties directly to John's question. It's my understanding that like causal inference is the most theoretically sound when the covariates of interest are directly measured and we have confidence in them. But the idea of looking at causal covariates that are themselves derived from models, and there's error associated with that approximation, seems like the causal effect estimates must be less certain. So I was wondering how do you kind of deal with that guess propagating error or greater uncertainty in the causal effect estimates?
Very excellent question. We haven't solved it, and you're exactly right. But yes, we do perform all of these measurements, but these are primarily coming from lexicons like entities. Yeah, NER is a model, both score is a model, but the rest of the properties, they are, yes, indeed measured on data, but they are it's a direct measurement, right? So it's like an aggregate for how long the tweet is spreading, right? So these are not coming, the majority are not coming from the models, but we haven't solved we haven't solved the uncertainty and how to incorporate it into the causal model from the predicted covariates
I see. I mean, I've put like moral foundation sounds like there's a lot of uncertainty there. So
Yes. Yeah.
So do you just report the effect, the causal effect from that as assuming that the moral uncertainty tag is kind of 100% accurate, or
exactly, okay. which has limitations. Don't disagree. Yeah.
Mm-hmm. And I simply, my question was very simple. Like, have you looked at different domains, or was it picking out some causal relationships that are specific to a given domain? Like, results are just COVID, or do you think they will generalize to other domains?
Very good question. Yes, we did. So we did it for the white helmets and for Venezuela, and they indeed generalize. So not everything, right? Something is domain specific, like depending on the campaign, but the verified user generalized as far as I remember. I mean, we did it like a year and a half ago, but yes, some definitely generalized. The disparity of spread, the effect on the disparity also generalized. Yeah. So we did multiple. Any other questions? Okay, cool. Let me tell you about more NLP-oriented work. This is another project where we learning global proliferation expertise and capability evolution from open source data. So imagine you have a scientific literature from like Scopus, Web of Science, OSTI, Google Scholar, right, Wikipedia, and also like other multilingual data sets. And then you take all of this data, and your goal is to extract content and context. So content is scientists and venues and institutions and countries, and this is a dynamic graph, right? And in addition to that, you can look into the abstract of your paper or the actual paper, and you can extract topics and keywords and different concepts that are tasks and data sets, methods, and embeddings, of course, right? And then when you extract this structured hybrid representation, I don't call it a knowledge graph, I call it a structured graph representation, a hybrid representation, and you use it to develop descriptive, predictive, and prescriptive analytics. And this is the type of augmented intelligence that I was talking about earlier. We need to make sure that the models are usable, right? And they are useful, and then they are helping the mission, right? We did this kind of the pipeline to go from public data to information to knowledge, understanding, and wisdom in two domains, AI and the nuclear domain. And I'm going to show you some results of the augmented technology, intelligence techniques that we developed. So NLP is not very, I mean, it's very off the shelf, I should say. At this point, we're developing a new model with CMU and UW right now to extract useful key phrases from the paper that are representative of that paper. But what we do, we basically collect terabytes of scientific literature. We perform topic modeling to basically remove false positives and clean it, and we learn embeddings to cluster this data better. And then we perform a variety of NLP enrichments as semantic role labeling, co-reference, part of speech tagging, parsing. And then this all goes into our graph construction pipeline, where we construct a single graph per paper of concepts, and then we construct global graph across multiple papers, and we pair it with the context, like the scientists and institutions and venues. And in addition to that, you know, like when you construct these graphs, they're super messy. You have to do entity resolution and disambiguation. So what we did, we developed a tool for like human in the loop entity resolution and disambiguation that I believe I will show you here later. So this is the first step, the topic modeling. So we had this data of like Scopus and Web of Science and OSTI and Google Scholar, and we run a topic model. And I'm showing this example for the nuclear domain. We have collaborators at the Berkeley lab who helped us to look into these topics and say, okay, this is not related to proliferation, this is medical, this is not, it should not be here, right? So we started with like, I know, hundreds, thousands of abstracts in this case, and then we rigorously filtered it. And then we build this content and context graphs, and these are the examples, right? So this is for Scopus, only one resource. We have more than 10. And then we started with this nuclear keywords, like when we sampled, then we did the topic modeling. And then on this slide, we kind of show different relationships between papers and scientists and journals, conferences, funding agencies in this case, and so on. And then for the content graph, we look into different, again, nuclear keywords or tags like nuclear fuel or nuclear material or fuel cycle and the relationships across papers. So this is the entity resolution tool that I mentioned, developed by our team, where we do it as the last step in our NLP pipeline when we disambiguate institutions and locations and scientists, especially with these are non-English names. It's impossible to disambiguate. So it's a semi-automated approach. It's not like all manual, otherwise we will die with this much data. But that helps us to use embeddings and kind of look into the overlap of different concepts and merge entities or unmerge, disambiguate in an informed and effective way. And then another tool that we haven't published yet, it's like fresh from the development, is the expertise search, right? So I showed you that, okay, we did use a lot of this NLP to build this structured representations, but why are we doing it, right? Like this is the most important question I think anyone should answer, why, right? The intent is to enable expertise search. So if there is an analyst he should have an ability to easily perform top-down or bottom-up analysis and search for experts, search for capabilities, track the capability of evolution over time across different countries. And that's what we're doing here, right? So this is shown for the ACL domain. So we leverage the ACL ontology, and we constructed similarly content and context graphs, but you can search for the scientist, you can look into who this person published with, and then you can have different representations of the graphs. You can have like a matrix representation, you can have a hypergraph, you can have a normal graph. You can perform different projections of these graphs on the scientist or on the, I don't know, on the institution and other variables, and see who publishes with who more often. Then you can do this temporal analysis of publications, right? When I published with someone, or you can also look into the actual content and what I published about, right? Like what kind of capabilities, is it sentiment, or is it, I don't know, information operations or something else? In addition to that, you can go and look into different paper properties, right? Like for this crowd of people, right? For the co-authors within this query. And you can kind of go and get these details on demand across multiple domains, not only ACL, but also nuclear and other domains. This is the example of the local graph, where for each paper we run NLP, and this is the model that we're developing with UW right now with Yulia Tsvetkov's team, to make sure that we extract useful information from the actual paper. So this paper is about an LSTM, and it was applied to sentiment analysis, and it was applied on this data set, right? So kind of very, very useful. What we as scientists, we are interested in this level of summary for the paper. So that's, again, another example of an augmented intelligence capability that is needed after you develop your AI, right? After you develop your brain, you need to make sure that this brain is usable. So I am gonna go to the next slide, and I will briefly mention this one. So I think I kind of like gave a spoiler alert for predictive analytics. So there is one thing is to be able to build this structured representations at scale, but there is another way is to use them and predict future collaborations and future interactions. So we designed this task as predictive analytics, where the goal is to forecast the evolution of global expertise and capabilities from these structured representations. And we use temporal graph networks and transformer models in this case, where we apply either discrete or continuous input features, and then we play with different types of node features. And the novelty is coming that this is the first work that is doing it on different nodes and edge types. There is really cool work from Leskovic's team, and then was the heterogeneous graphs. I believe it's T-event model or something. And there is a really cool work from Twitter that we use as a baseline that is using this continuous inputs. It's kind of they basically feed them an adjacency list into your model. And then, but what we bring to the table is we kind of predict in different types of edges, and our nodes are heterogeneous, and we leveraging the node features that previous models have not really took advantage. And we perform multi-step forecasting, and we report our results in a transductive and an inductive fashion, right? So basically, what is my performance for the nodes and edges that I have seen before and I have not seen before? And that what we found is again, this is one slide, but I wanted to highlight that this is human behavior, right? This is predicting future publications and future collaborations. What we found is that these models, the performance varies across different edge types. And when we are trying to forecast scientist to scientist edges, which is a harder task, both models are better with continuous inputs than discrete. But then when you try to predict scientist to institution or scientist to capability links, so basically scientist in institution is like, if I publish with ISI next, right? And then scientist to capability would be, if I publish, will I publish on a transformer model, for example? We found that discrete inputs are actually better than continuous. And we believe, we're still investigating, this is like work in progress, but we believe that it deals with fundamentally with the way that human are collaborating on generating knowledge, right? Because this is a knowledge generation process, like publication patterns. So there is this knowledge that is evolving over time, and there is this a generative process of the knowledge when people are collaborating and developing this knowledge, right? Inventing this knowledge. So there is it's very interesting. And let me jump to the last part of my presentation is about prescriptive analytics, where we applied our causal discovery and inference techniques to the publication domain. And again, to this crowd, I don't need to sell the importance of prescriptive analytics. We need to go beyond correlations. We need to go beyond answering the questions, what has happened and what will happen, right? So what will happen is predictive, but we really need to answer the question, what will make X to happen, and understand how the past, present, the future cured, and how to direct future outcomes, right? So we want to be proactive. In this case, instead of messages and users in a social network and information campaigns, we have scientists and institutions and research focus and publication properties and funding influences. And we have current and previous behavior of publication, and we have future behavior. And then similarly to before, we're using an ensemble model that we have that includes constraint-based methods and score-based methods, which is a causal ensemble paper from NERPS. And in addition to that, in addition to causal discovery, we do treatment effect estimation, and we use again off-the-shelf tools, off-the-shelf techniques, a very popular causal forest from Stanford, propensity score matching, and Vein. And we evaluated on multiple domains on the nuclear domain and the AI domain. So imagine we started with like thousands of papers, again, thousands of scientists, and we have their research keywords, if you wish, right? And then we run it on 5 years of data. AI, in our case, is an out-of-domain evaluation, and the nuclear domain is in domain. And then we report, and we only did it for like 2 sources, OST and ACL. But there are more sources in working right now. So what are the treatments, covariates, and outcomes? In this case, the treatments are different publication concepts like, I don't know, nuclear facility or high enriched uranium for nuclear. And then for AI, it was like NLP, transformers, causal explanation, LSTM. So it's a mix of techniques and methodologies and approaches. And then in addition to that, we have location as a treatment. And we have adoption or maintenance or retirement of research in previous years. And then let me first tell you the outcomes. Our goal is to measure the effect of these treatments on 4 things, actually. One is adoption. Adoption means I will start publishing on a specific capability, right? What makes me start publishing on a transformer? Maintenance is I published on non-English, and I am going to continue publishing on non-English, let's say. Retirement is that I completely stopped publishing on LSTM, right? So this is stop publishing. And then in addition to this three outcomes, we have productivity, right? What affects the productivity of a scientist? In terms of the covariates, we have a variety of author properties, and institution properties, location properties, and publication properties like length and readability, things that we can infer from language from the abstracts. So this is an example. Again, similarly, we run the causal discovery model, and then we find really interesting really interesting findings for the AI use case. If you publish in German, then you will maintain publishing in like across non-English languages. If you publish on causal, you will start publishing on interpretability. If you publish on Arabic, you're gonna continue publishing in multilingual NLP, right? So these are very interesting findings, and this work was just presented at the EMNLP workshop on causality. And there is another paper that we published on visual analytics aspect of this work. So the next slide is kind of looking deeper, right? So we can kind of see a strong consistency of influence of longer publishing on the same topic, and inconsistent influence on continue publishing on the same topic, depending on the topic, right? So explanation, if you start publishing, it's a hot topic right now, so you keep publishing. But if if you publish on multilingual NLP, it doesn't mean that it will keep publishing on multilingual NLP. And then for the nuclear use case, I mean, I think it's less interpretable here, but we show similar findings, right? When what effects that, for example, just an example, publishing on a critical accident influences starting to publishing on nuclear security and continue to publishing on fissionable material. So these are the results, and there are more insights in this paper that Maria just presented at EMNLP. And the last point I want to make is it's really important to, I mean, yes, we're all developing great AI, but it's really important to ensure that we can trust AI and we develop it in a responsible fashion. So my team had been doing a lot of work in this area, and we published a lot of papers there by developing different techniques and methodologies to really evaluate the robustness of the models, accountability, benchmark these models, fairness of these models using causality. And all, like, these are all of the papers that are coming from my group. What I wanted to also highlight is that quantitative evaluation is not enough. And a big contribution from our group is developing these widgets. These are Jupyter notebooks that we have we embed these widgets in Jupyter notebooks, and when we compare different causal structure learning algorithms, so causal discovery methods, we can do it in interactive fashion, and we can really go and look into the data and really understand why model is making this prediction and open that black box. So this is the team behind this current project on non-proliferation. And I just want to mention that we have a great national security internship program that when we always looking for brilliant interns. And I hosted over my 6 years in the lab, I hosted more than 20 interns, hired 3 of them who became scientists in the lab. And it had been a really productive collaboration, and we did a lot of great science together. So the last thing is to thank the sponsors, obviously, and I really appreciate your time, and I really appreciate the invitation. I'm looking forward to your questions, and I'm looking forward to meeting with the students.
We have a few minutes for questions. If anybody has questions, I think now is the time to bring them.
Oops, sorry, I have a question or something, because thank you. This is a great talk, and actually cover a lot of the same questions that we are interested in, causal discovery.
Yeah.
So one thing we are actually coming up against is that when you're using like Twitter data, or kind of even scientific papers, but Twitter data, for example, it's a language, right? And you're trying to measure the outcomes and covariates and the treatment. They're all basically in language, so they're not completely separable and independent. So I know there is some papers like trying to kind of causal language, this discovery, but I wonder if you consider that impact of this non-independence of the.
That's yes, it's a problem. I don't know whether you are you familiar with the question that happened at EMNLP? Are you?
Sorry, my dog. My dog.
Totally fine. No. Are you familiar with the EMNLP workshop that just happened on causality with language, was like high dimensional? There is a really cool paper that Jacob Eisenstein and the group from Google.
So the Jacob Eisenstein series.
Yeah. So they started thinking, but I'm telling you that the community is really like in the beginning of trying to disentangle this. Like, we haven't solved it yet, but not everything is coming from language. Some, and there are issues, right? But we're also looking into like other treatments and covariates. But you're right. It's very emerging, and there are many issues with it. And every time we report the results, there should be an asterisk that yes, this is.
Like we looked into it and then kind of gave up because the fundamental problem is there's no ground truth. So even if you do something, how do you evaluate it?
Exactly, and that's why having the ground truth, like performing on the ground truth, really helped, because we did have like 4 scenarios provided by different teams, not us, right? that we developed this ensemble model and we evaluated on the ground truth. And in addition to that, we did internal evaluation, and then it's in the NERPS paper where we just basically like generated everything and anything possible, right? Like from different distributions, and we did have the ground truth. But you're right. I mean, this is computational social science, right? In one case and in another case, and then yeah, there is not, I mean, there are social theories about human behavior, but yeah, how are you gonna measure it, right? And how are you gonna, yeah.
I had another question. I am curious, especially about the causal work on misinformation networks. I'm curious what the implied interventions are, because it seems to me that a lot of the variables that were studied are specific to the message or the user, and these are presumed malicious actors. And if we are performing interventions, we are not the malicious actors. And so what does this causal model tell us about how to restrict the flow of misinformation or intervene in ways that will have a positive outcome?
Very good question. So depending on what type of intervention you want to make, right? If you want to make an offensive intervention, I mean, you can you can generate fake accounts, and you can generate different content, right? Like fake content, right? And you can intervene that way. You can generate content with like specific moral foundation. So this is an offensive intervention. That's what you noted is, I mean, that's what we're looking into right now. But there is a defensive one, right? Which is more like policy oriented and just like knowing, and that's what we taking. We are not recommending, right? I'm not saying that, oh, I'm recommending you the intervention. I'm not a social scientist, I am a computer scientist. I think in order to truly recommend interventions, we AI people can give this algorithmic findings to the political scientists and social scientists and policy people who would then recommend interventions, right? So I don't believe AI people can solve it by themselves, absolutely not. But at least it was the cognitive security, I really wanted to move beyond the what question and really measure like why some things are spreading. Is there generalizability? It was a great question from Christina, right? Across campaigns. Let's say if there is like a specific country that has a campaign in Syria and Venezuela, do they use the same tactics? Can we pick it up, right? And then when the social scientists will come, they have theories that they can probably explain our findings, right? So I truly believe it's a teamwork and multidisciplinary work.
Thank you.
Yeah. Okay, this had been great. Thank you so much for the invitation. It was my pleasure. And I would be happy to share, like, all of it is public, and if there is interest, I would be happy to share any or paper.
Yeah, can you share slides with us?
Absolutely, absolutely.
Great, thank you so much.
Yeah, thank you.
So thank you. Thank you for the great talk. I think we have a few more individual meetings and group meetings, and we will see you again and discuss more.
Yes.
Thanks everyone for attending the talk. See you again in the next session.
Thank you. Talk to you later. Thank you so much.